let's talk a little bit about normal forces and friction forces. That's how surfaces interact, and we deal with these forces quite often. Here I have a surface, and if I put a physics textbook on top of my surface, now it's being held up by a normal force. How do we know? Well, there's a force of gravity acting on our physics textbook. The Earth doesn't stop pulling on that textbook just because it's sitting on the table. But the textbook's not going anywhere, it's just sitting there. So there must be an upward force equal to the weight of the textbook, in this case, to prevent it from moving. It's just at rest. So we have a normal force pushing up right now. What would happen if I drop another textbook on top of this one? What just happened to my normal force? Well, it's got to get bigger. Because now the surface is holding up two textbooks. So it is applying a larger force to the bottom of that physics textbook. And if I keep putting books on top, this force will keep getting bigger and bigger. And this will keep happening. The surface reacts and pushes up with a bigger and bigger normal force until what happens? Until the weight from all this stuff is just too much for the surface to hold up. Maybe my table is made of wood, and the bonds that hold the wood together at some point won't be able to hold on to each other anymore. There's so much weight, and the wood will crack and break, and all my books will fall through the table. But until that point, the surface reacts and keeps pushing up with a bigger and bigger normal force. And you might wonder, how is that possible? So we can take a look at a simple model of what the surface looks like. In the simplest terms, the surface is a bunch of atoms connected together with bonds. If we zoomed in with our microscope and we kept zooming in, eventually we would see that the surface is made up of atoms connected by bonds. And if we think about each one of those bonds like a little spring, and if we try to pull the atoms apart, the bond stretches and wants to pull them back together. The bond has a certain length it wants to maintain, kind of like a spring. So if we take our surface and we zoom in to the microscopic level, we've got atoms connected by springs, basically, bonds. If we set something down on top of our surface, what's it going to do? It's going to sink into the surface a little bit until the springs stretch just enough that they're pulling back up with enough force to hold up our box. So this would look something like this. If you think of it like springs, kind of like a trampoline, right? If one person stands on a trampoline, it bends in, it deflects a little bit, and just enough to hold that one person up. If a second person walks out, stands in the trampoline, what happens? It sinks a little lower until there's enough force to hold up those two people. And so if we think of our surface as a bunch of little springs connected together, as you put more and more weight on top of the surface gets deflected ever so slightly at the microscopic level, gets deflected a little bit, and those springs get stretched and they want to pull back up. How do those springs pull back up? Perpendicular to the surface, normal to the surface. And they create a force straight up and hold up the weight. And as we put more weight, the springs stretch more until they've stretched enough to hold up that weight. And this keeps happening until we exceed the strength of those bonds and they break, and then everything falls through. We don't have a surface anymore. So that's a model. Are models always correct? No. But hopefully they're useful and helpful. So if this model helps you picture, helps you get a grasp of why a normal force reacts and can be bigger and bigger, and why it adjusts as we put more and more weight on the table or take weight off the table, how does that normal force adjust? If this gives you some way to kind of wrap your mind around it and picture what's going on, then it's helpful. It's a model. It's not exactly what's going on, but if it's helpful, that's what's important. The other thing we want to look at is friction. And again, we're thinking about how these two surfaces are interacting at a microscopic level. If we zoom in with our microscope, our surface doesn't look like this. It has some roughness to it. If we zoom in close enough, our surface is going to look more like this. And our block will also look rough and jagged like this if we zoomed in with our microscope. And if we try to drag our block across our surface, well, what's going to happen? These nooks and crannies might dip into each other and press. We might get a surface pressing up against another surface, like we're getting maybe right here. Well, what is a surface pressing up against another surface? That's a normal force that we just talked about. So if we try to pull this block to the right and it catches on some surface roughness and we get a surface to surface contact, we'll get a normal force there between those. And a normal force can react. If we pull with a small force, we pull with 1 Newton, this will push back with the force of 1 Newton right there where that interaction is in the red circle. If I pull with a force of 2 Newtons, this will push back with 2 Newtons because it's a normal force. It can react. It'll get bigger and bigger. And this box won't move. We call that static friction. As we pull on our box with more and more force, the box stays at rest. The friction force reacts and gets bigger and bigger and bigger. Because really, if we zoomed in at enough of a microscopic level, it's just a normal force. It's two surfaces pressed up against each other. So if we were to plot friction, the friction force as a function of our pulling force, and this is our pulling force right here. If we pull, like I said, with 1 Newton, friction force 1 Newton, 2 Newtons, 2 Newtons. So as we increase our pulling force, the friction force increases until we pull hard enough that our block will jump out and dislodge itself from the surface and slide across it. And then we have motion between our surfaces, right? There's sliding. We call that kinetic friction. And at that moment, when the box, we pull hard enough that the box dislodges and slides, we go into that kinetic friction mode, and the friction force looks something like this. And it doesn't matter how hard we pull now or how fast the box is moving, the friction force remains constant after this. So this is static friction in this region here. And this is kinetic friction. Static means not moving. The two surfaces are stationary with respect to each other. Static. There's no sliding, no slipping. There's none of that. Kinetic means motion. Relative motion. The two surfaces have relative motion with respect to one another. There's sliding or slipping. There's motion between the two surfaces. So static friction, we don't know what the friction force is right away because it could be anything, right? It reacts, kind of like a normal force. There's not a formula for normal force. You have to look and see how much weight am I putting down and do a calculation and see how much the normal force is pushing back up. Same here, but we can calculate the maximum static friction force. So I use a subscript S for static friction, and this is always going to be less than or equal to its maximum value. And the maximum value depends on, what do you think it depends on? It depends on the surfaces. Some surfaces are smoother and have less friction. Some are rougher and have more friction. It depends on the surfaces. That's this coefficient of friction, mu, the static coefficient of friction between those surfaces, and that depends on the surface. If you make something out of Teflon, it's going to have a much smaller coefficient of friction than if you make it out of steel, something like that. What else does it depend on? It depends on how much those surfaces are interacting. How hard are those surfaces being pressed into each other? And what tells us that? The normal force. The normal force is the interaction between those two surfaces, how hard one is being pressed into the other one. So that gives us our maximum static friction force. And the kinetic friction, F sub k, we can calculate it. It doesn't change. It doesn't matter if the box is sliding at 1 meter per second or 50 meters per second. It doesn't change. And it's mu k, the kinetic coefficient of friction, times the normal force. And these are different. The static coefficient of friction and the kinetic coefficient of friction are different. And if you look at our graph here, you can see that the static coefficient of friction is going to be a little bit bigger in most cases than the kinetic coefficient of friction. Typical numbers we see for static coefficient of friction, things like 0.3, 0.4, 0.5, and in that range. And for the kinetic coefficient of friction, somewhere around 0.1, 0.2, maybe up to 0.3. Those are typical numbers that we see in our physics problems. What are the units for coefficient of friction? Well, this is force, has units of newtons. This is force, has units of newtons. So the coefficient of friction is a unitless quantity. It's a ratio, it's a unitless quantity.